Hi everybody, and welcome to the first video for Chapter 16. This is a video on Section 16.1, which is an introduction to a study of probability. So before I dive into what this section in particular is about, let me discuss briefly why we're studying probability. Probability is a study of the quantification of uncertainty. So suppose you want to try to quantify things like risk, or quantify things that are uncertain. The tool that you use to do such a thing is probability. And quantifying risk is something that lots of people want to do. In particular, the entire insurance industry runs on trying to quantify how much risk somebody poses. Okay, so probability is extremely important in the real world because it's the primary tool for trying to measure and quantify uncertain things. Furthermore, probability is entirely necessary to having a deep understanding of statistics. So chapters 14 through 16 are our probability and statistics section. And if you ever read any sort of statistics literature, maybe you're a psychology major and you read a psychology study that uses statistics, that statistics will most likely run on probability. Okay, so probability is an extremely important field of study. Now in section 16.1, all that we are going to do is introduce some terminology for probability. So we're going to talk about sample spaces and events. Okay, so as I said, this section is mostly about just vocabulary and terminology. So here is the first term to understand. A random experiment is an activity or a process whose outcome you can't predict ahead of time. So think about things like tossing a coin, rolling dice, trying to predict the weather, things like this. Okay, you can't predict what's going to happen ahead of time. That's a random experiment. Associated with every random experiment is a set of all possibilities. What could possibly happen? What are the possible outcomes? The list of all of the possible outcomes is the sample space. So think about tossing a coin. Right? If you toss a coin and I ask you, what could possibly happen? Can you give me a list of possible outcomes? You would say, well, sure, I can. You either flip a heads or a tails, and that's it. Right? That's the sample space. Or suppose that you're going to draw a single card out of a deck of cards, and I ask you, what could possibly happen? Could you please list for me a complete list of possible outcomes? You would say, well, sure, I can. There are 52 possible outcomes because there are 52 cards. So that's the idea of a sample space. An event is a subset of the sample space. So an event is a collection of some possible outcomes. So the sample space is very broad. It captures every possible outcome. The sample space is all possible outcomes. An event, on the other hand, is just some possible outcomes. So again, think about drawing a card out of a deck. You could consider the event drawing an ace. Okay, drawing an ace, that event has only 4 possibilities inside of it because there are 4 suits. Or think about drawing a 2 and drawing a 7. That event has 8 possibilities in it. So that event has size 8. Okay. So in this chapter, capital S, will always denote a sample space, and capital N will always denote the size of the sample space. And by size of the sample space, I mean the number of possible outcomes for the particular experiment you are performing. The first canonical example of a random experiment is tossing a coin, and as we've already said, if I ask you, you toss a coin, what could possibly happen? The answer to that question is, I either get a heads or I get a tails. Since there are 2 possible outcomes here, N is 2. Suppose now that you flip a coin twice and you record what you see after each toss. The sample space now is, well, I could flip a heads and then a heads and then a tails and then a heads, or 2 tails. So that's the sample space here. There are 4 possible outcomes, so N is 4. Okay, so I want to pause here and say that if you're ever asked what a sample space is, The answer highly depends on the description of the experiment. So here it was explicitly said, you record the outcome of each toss in the order you see it. So heads heads, heads tails, tails heads, tails tails are all different outcomes. You care about the order in which you flip things, and you care about what you flipped. So keep that in mind. If I give you this experiment and say what could possibly happen, here are the 4 things that could possibly happen. Suppose now that you toss 2 distinguishable coins, like a nickel and a quarter, at the same time. This random experiment on the surface looks different from the one we just described, where you toss a single coin twice. But notice that the sample space is the same. It's just the interpretation is different. So here a heads heads means that the quarter flipped heads and the nickel flipped tails. And heads tails means the quarter flipped heads but the nickel flipped tails, and so on. So even though on the surface this appears to be a different experiment, it actually really isn't. The underlying sample space is the same. So since those last 2 experiments have the same sample space, we will just consider them to be the same. Now let's consider a different experiment. We are going to toss a coin twice, but now we only care about the number of heads that come up. So now we don't care about the order in which you flip anymore. All we care about is counting the number of heads that we see. So again, you have to imagine yourself doing this experiment and so think about doing this experiment and writing down the number of heads that you saw. What could you possibly write down? Well, if you flip a coin twice, you can either see 0 heads, or 1 head, or 2 heads, and that's it. So it wouldn't make any sense here to write the number 4 because you only flip the coin twice. If you flip a coin twice, you can't see 4 heads from that. Here is another example. Your favorite basketball team is down by 1. The clock is expiring. One of your teammates is fouled and goes to the free throw line to shoot free throws. And let's just assume that the game is riding on the outcome, so maybe the clock has just 0.01 seconds on it or something. Okay, so here you want to consider the shooting of the 2 free throws to be the random experiment. I'm going to shoot free throw 1 and then shoot free throw 2. What is the sample space? Well, it kind of depends on what rules you're playing by. So there are 2 different scenarios here. The first scenario is sort of an NBA setup, and the next scenario will be a college rules setup. In the first scenario we'll consider, your player gets to shoot 2 free throws no matter what happens. So if this is the case, you can argue that the only thing that matters is how many free throws this teammate makes. If you make them both, you win. If you miss one of them, then you tie and go to overtime, and then if you miss both, you lose the game. So if all you care about is the number of makes the person has, here is the sample space. You either miss them both, you miss one of them, or you make both of them. On the other hand, think about what happens in college sometimes. Your player is shooting in 1-and-1. This means that the player gets to shoot the second free throw only if this player made the first one. So in this case, there are also 3 possible outcomes, but the circumstances are different because the order in which you make or miss matters. Because if you miss first, you don't get a second try. But if you miss second, that means you made the first, so you had 2 tries. So in this case, you can write the sample space like this, where F is like a fail for miss, and S is like a success for make. So if you fail on your first shot, so you miss your first shot, you don't even get a second shot. But if you make your first shot, then you get a second chance, and you either miss or make on your second chance. Okay, the most common scenario when rolling a pair of dice is to consider only the total of the 2 numbers rolled. This is what happens in most casino games. In this situation, we don't really care how a particular total comes about. So rolling a 7 simply means that the total of the dice is a 7. And usually, for most casino games, it doesn't matter if you roll a 3 and a 4, or a 2 and a 5, or a 1 and a 6. All of those are considered the same. So if this is the setup of your game, the sample space looks like this. If all you care about is the total of the two dice, here are the possibilities for the total. If you roll 2 6s, you get 12 points. If you roll 2 1s, you get 2 points. And then any number in between is possible, any whole number in between. So if you don't care about what the individual dice roll, you only care about their total, here is the sample space. On the other hand, maybe sometimes you do care about what the individual die rolls. For example, in certain bets and craps, 2 4s wins, but a 5 and a 3 doesn't win. So even though 2 4s and a 5 and a 3 both give you an 8, you distinguish between those two different outcomes. So now if you care about what each individual die rolls, here is your sample space. It's a lot bigger because you're keeping track of what each individual die rolls. So the first die can roll a 1 and the second die can roll a 2. Or the first die can roll a 3 and the second die can roll a 1, etc. Now there are 36 possible outcomes if you care about what each individual die rolls. Notice that the dice are colored red and white. This is a symbolic way to emphasize that we are treating the dice as distinguishable. That's why these two rolls here are considered different. Okay, there are 2 examples left here, or I guess maybe this is the last example. This is an election example. 5 candidates that we will just label as A, B, C, D, and E are running in an election. The top 3 vote getters are chosen president, vice president, and secretary in that order. So what does that mean? That means that the top vote getter becomes president, the second most votes getter gets to become vice president, and the person who got the third most votes becomes secretary. So such an election can be considered a random experiment with sample space ABC, where this means A came in first, B came in second, C came in third, or things like ADB, so A wins, D is vice president, and B is secretary, and so on. So we'll talk about how you can count this in a later section, but here there are actually 60 possible outcomes here. There are 60 possible ways for this election to turn out. You don't, in general, want to write down all 60 ways. Right? That would be time-consuming and kind of tedious. That's why we have a ... here. So a ... essentially means, look, you understand what's going on now, right? I'm going to list all strings of length 3 that have 3 different candidates in them. Those are the possibilities. Yeah, so notice that order here matters. ABC is different from BAC. In this outcome here, A wins. In this outcome here, B wins. The sample space has size 60. Okay, you don't want to write 60 things. So when a sample space gets big enough, you just use a ... to emphasize that you're not going to write everything. That previous example illustrates the point that sample spaces can have a lot of outcomes in them. That particular example had 60 outcomes, but you can think of random experiments that have millions of outcomes. Okay, and you don't want to write down a million things. That would take forever. So you can use a ... if you want to. The key thing is to understand what the sample space looks like without necessarily writing all the outcomes down. So in this previous example, we had a feel for what the sample space was. It's just, strings of length 3 where the 3 letters are different. Okay, because you can't have A. You can't have A getting all 3 positions. In future sections, our real goal will be to find N, the size of the sample space. Because when we do probability calculations, we'll need to know how big a sample space is. So sometimes if the sample space is small, you can just write it down and count. But like in this example here, you don't want to try to write everything down. You'll probably miss some to begin with, but it's just sort of tedious and time-consuming. So in section 16.2, we will talk about ways that you can count the sample space without just writing everything down. Okay, so that is the conclusion of section 16.1. In the next section, we move to counting sample space sizes. And once we know how to count the size of sample spaces, we will be in a position to study probability itself in section 16.3. So that is all for now.